Hi there. In chemistry, we represent chemical substances as chemical formulas. In a chemical formula, you should be able to note that we have got an element and different numbers that are written at the subscript of that element. These subscripts just indicate the number of atoms of a specific element. And when we're talking about molecular and empirical formulas, this becomes very important. If you notice here, when we divide by 6 throughout, we're going to have CH2O, which is another formula which we can say is glucose. The first formula we looked at is known as the molecular formula, while the simplified version of the molecular formula is what is known as the empirical formula. This is Z Online School. In this video, you and I are going to be looking at more concepts involving molecular and empirical formulas. We're going to do this in a systematic way, and by the end of this video, you should be able to know how to work out percentage composition, determine empirical formula, and also determine molecular formula. At the end of this video, we've got bonus tips. Make sure you watch this video till the end to get the maximum value out of it. Let us begin with talking about percentage composition. To start out, let's talk about composition. What does it mean? Composition is a word that means the different parts which something is made of. So when we're finding the percentage composition, we're finding a part as a percentage of something. In chemistry, this something is a compound. These different parts are elements or compounds themselves. One thing I would like you to note is that in mathematics and science, percentage is like a fancy way of rating something on a scale of 1 to 100. So if you've ever done things like rating something from 1 to 10, 1 to 50, working with percentage won't be something very difficult. Percentage composition should always be remembered to involve masses. It's rare that percentage composition might involve other physical quantities. Usually, percentage composition is going to involve masses only. Percentage composition can be defined as the percentage of an element's mass in a specified compound. Now, let's talk about the formula of percentage composition. Without this formula, we can't do anything much. Percentage composition, like we talked about, is the percentage of an element's mass in a specified compound. So the first thing we need to know is the mass of an element in a compound, and we're going to put it as the numerator. Then the denominator is going to be the molecular mass of that specific compound in which a certain element is found. For example, we have water. Water is made up of 2 hydrogen atoms and oxygen. When we want to find the percentage composition of hydrogen, we're going to find the mass of hydrogen in water and divide it by the molecular mass of water. Then we multiply by 100%. The answer we're going to get is known as the percentage composition of that hydrogen. Sometimes this will be abbreviated as AR over MR. So whenever this is used, don't get confused. Let's look at some 2 examples for us to understand percentage composition even better. In the first example, we're asked to calculate the percentage composition of water in copper 2 sulfate crystals. This question we have here is elaborate enough. The first thing when we're finding the percentage composition, like you heard me say, is the mass of the element in the compound. Now, one thing strikes in this question. We're not finding the percentage composition of an element. Rather, we're finding the percentage composition of a compound. So we're going to find the mass of this compound water. How are we going to do that? Well, just like we do for finding the molecular mass for water, we'll do the same. We need to identify the elements present in water, that's hydrogen and oxygen, determine the number of atoms. In this compound, we've got 10 atoms of hydrogen. However, in water, we have 2. So for now, let's use that 2. Oxygen has 1. Later, we're going to use this 5 when we begin calculating the percentage composition. But for now, we're just calculating the molecular mass for one molecule of water. Then we multiply by their respective relative atomic masses. Hydrogen is 1 and oxygen is 16. We find the sum of 2 and 16 and we have 18 grams per mole. Next, we also do the same for the hydrated copper 2 sulfate. We determine the elements. There's copper, sulfur, oxygen, and hydrogen. So I think we can determine the number of copper and sulfur. You can see that both of them are just single atoms. Now we go to oxygen and hydrogen. Oxygen has got 4 in the copper 2 sulfate, while in this water it's got 5. When we add that 4 and the 5, we get 9. Hydrogen has got 10 because this 5 multiplies with that 2. It's very important to note this difference. When we were calculating the molar mass for water, we never included the 5 because water does not have that 5. If you were to find the molecular of water or ask any teacher the molecular mass of water, you find that it will be always 18. That's why I'm avoiding to use that 5 and multiplying it by the 18. It will give us a wrong conception of the molecular mass of water. Now, we multiply these respective elements by their respective atomic masses. Copper, as you can see, is 64, sulfur 32, oxygen 16, hydrogen 1. It would be very helpful if you knew the 20 elements by memory. You can easily find questions faster. So let me speed up here. We're going to find the answers like that, find the sum. This shouldn't be very difficult because you have obviously watched our videos in order. This 250 is the molecular mass for copper sulfate that is hydrated. Now, our job is to find the percentage composition. Remember our formula, we need our mass for the element. This time we're finding the percentage composition of the compound, so the mass of the compound in the bigger compound divided by the molecular mass of the whole compound. You must note that this point when we're finding the percentage composition is when we multiply by the 5, because we have 5 molecules of water in this hydrated copper 2 sulfate. Okay, that's the answer. We've got 90 grams. We are going to divide this answer by 250 and multiply our final answer by 100. You can see it gives us 36. Hence, we found the percentage composition of water. Very simple. One thing you should pay attention in this example is how we didn't use this 5 to find the molecular mass for the water. We only used this 5 when finding the percentage composition because this 5 plays a role in the composition of water in the hydrated copper 2 sulfate. However, this 5 does not affect the molecular mass for water independently. Now, let's look at a second example. In the second example, we've been told an ore of aluminium contains 25% by mass aluminium oxide, which is written as Al2O3. Calculate the mass of aluminium in 200 tons of this ore. In this question, what you must pay attention to is that we've got the percentage composition of aluminium oxide in the ore. Simply put, aluminium oxide does not occupy these 200 tons totally. It only occupies 25%. Therefore, to find the actual amount of aluminium oxide we're working with, we need to find the mass of aluminium oxide by applying the percentage composition. To do that, we're going to get the percentage composition and multiply it by the mass of the compound. The compound here is the aluminium ore, which is 200 tons. So the mass of aluminium oxide in this ore is going to be 25% of 200. What you see when working with percent is we always have this 100 being divided by the percentage we've been given. You can see that the zeros here cancel out and we're just left with a 25 and a 2. So mass is equal to 50 tons. Now, what we need to find is the amount of aluminium that is found in these 50 tons. This 50 tons represents the mass of aluminium oxide that we have. Therefore, there will be a certain mass that we're going to find that will be less than these 50 tons. For us to find that, we need the molecular mass of aluminium oxide. I'm just going to give you the elements here to save time, and you're going to find the molecular mass for yourself. I hope you paused the video. The formula mass must give you 102 grams per mole. Now let's work out the percentage composition. Again, we use our formula here. This time we're using the mass of an element. We don't have a compound, so mass of an element in the compound. The mass of aluminium is 2 multiplied by 27, which will give us 54. And then the molar mass or the formula mass of aluminium oxide is 102. We're going to multiply this by 100, and that's how we're going to get the percentage composition of aluminium. Now, since we have the percentage composition of aluminium, we can easily find the mass just like we did in the first place here. So the mass of aluminium is going to be 52.9% of these 50 tons. Again, you can see we've got that division by 100. Whenever you want to apply a percentage, always remember to make it over 100. Here we can see that we can simplify some things. 50 into itself is 1, so we can put a 1 there, and 50 into 100 is 2. Therefore, we're just calculating 52.9 divided by 2. And as you can see, our answer is 26.45. With this done under percentage composition, applying this information when finding the molecular formula and the empirical formula won't be much of a big deal. So let's begin talking about formulas now. What is the empirical formula in chemistry? Well, the empirical formula is simply a chemical formula that shows us the elements in their simplest whole number ratio. As you can see, some of these things here are just there to make the grammatical sense of this definition true. What you always need to remember about an empirical formula is that it's going to show our elements with their number of atoms in their simplest whole number ratio. For example, let's say we had glucose like we had in the first place. When we divide each element's number of atoms by 6, we're going to have a new formula, CH2O. This formula is what we call the empirical formula. Now, how do I arrive at this? Well, we need to take 3 important steps. The first thing is that we need to find the number of moles. The number of moles for each element. For example, in the chemical formula for glucose, we had carbon, hydrogen, and oxygen. We're going to be given information about carbon, hydrogen, and oxygen. That information we're going to be given from the question is going to be used to find the number of moles. Usually, this will be just the grams or the percentage composition of those elements in the compound. After we have found the number of moles, we need to find the simplest ratio. And therefore, we're going to get the smallest number of moles that we'll find and divide it throughout. After we do that, we need to make one important step. We need to check if our answers are simple whole numbers. With these 3 steps, I'm assuring you, you will get most of your empirical formulas correct. Let's dive into some examples so that you can understand this even further. Like I said, the first step is finding the number of moles. As you can see right from here, without reading the question, we've got some grams. Therefore, our mass formula that we've looked at in our videos is going to be very helpful in this calculation. We've been told the compound contains 4.5 grams of carbon, 0.75 grams of hydrogen, and 6 grams of oxygen. What is the empirical formula of this compound? Well, don't stress. What you just do is find the number of moles for each of these elements. Carbon. Our formula we'll be using is N is equal to M over Mr. I'm sure if you've been watching our videos in order, you understand how this formula comes about. Okay, our mass is M and our Mr is the molar mass. We're going to be using the molar mass of carbon here and the mass which has been given. Therefore, N is equal to 4.5 divided by 12. One thing you're supposed to note here is that whenever you're getting the molar mass, just get the molar mass for one single element. Even if an element is diatomic in nature, for example hydrogen and oxygen, just get the molar mass for one element. So for hydrogen, we're just going to get 1, oxygen, we're just going to get 16. Never make a mistake of saying this atom is diatomic, therefore I think the molar mass is going to be twice. If you do that, your empirical formulas will be wrong. If we work out this on our calculator, 4.5 divided by 12, we'll be given an answer that's very nice, 0.375. It will be very advantageous if you followed me along, got a piece of paper, got your calculator, and also did these calculations. Like that, you even learn better. Let's do the same for hydrogen. The mass has been given 0.75. We're going to divide by 1 because that's the relative atomic mass of hydrogen. And N will have 0.75. We divide any number by 1, we just have that same number. We do the same for oxygen. The mass is 6 grams. We divide it by 16. 6 divided by 16 is going to give us 0.375. Yes, it's actually 0.375. Our next step now is dividing by the smallest mole. Our smallest mole, if we look here, is 0.3. This is 0.3. These two numbers are the same. So yes, 0.375 is our smallest mole. Therefore, to find the number of atoms of carbon, we're just going to say C like that. Then get the 0.375 divided by 0.375. You can see that's not difficult. We do the same for hydrogen. 0.75 divided by 0.375. I think we need to do the one for hydrogen using a calculator. Okay, our answer is 2. Wow, that's very nice. And we can see oxygen is the same as the number we're dividing by, so nothing changes much here. Therefore, our empirical formula is simply going to use these numbers 1, 2, and a 1. The carbon is going to get a 1, the hydrogen a 2, the oxygen this one here. So the empirical formula is going to be CH2O. Very simple. I think you've seen this empirical formula somewhere, right? Yes, it's the empirical formula for glucose. Let's look at the second example. Wow, we've got percentages here. We have been also asked to find the empirical formula. One thing you notice that when we have percentages by mass, obviously these are percentages by mass, we just take them as grams. Percentage composition is going to be just taken as grams. Therefore, we're going to identify the elements that were being used. We've got nitrogen, hydrogen, sulfur, oxygen. They're quite a lot, but don't get intimidated by the number of elements. The procedure is going to be the same. We're going to find the number of moles. Nitrogen, 21.2. Molar mass. Nitrogen is diatomic, but we won't even dare to think about that. We're going to get the single unit molar mass, which is 14. Now we work out that. Okay, we have some number here with points. I think we can just round off somewhere here. We'll just get 1.5143. We work out hydrogen. Hydrogen has got 6.1. Hydrogen is the simplest, nothing changes, guys. So when you have hydrogen, just feel nice. You're just going to write what's on top again. Sulfur 24.2. As you can see, sulfur is 32. 2.42 divided by 32 is going to give us this number here. I think again we can just end on 0.7563. Now we go to oxygen. Oxygen 48.5 divided by 16. Okay, and we are done. The last answer here should be 3.0313. We have all the number of moles for each of the elements: nitrogen, hydrogen, sulfur, and oxygen. So we check which one is the smallest. I think it should be sulfur here, 0.7563. And so we're going to divide throughout by the number of moles for sulfur. N is going to be 1.5143 divided by the number of moles for sulfur. Okay, you can see our answer is 2.00. So we're just going to round off to the nearest whole number. Even if we rounded off to 1 decimal place, you can see our answer will still remain 2. So yeah, practically rounding off doesn't really impact our answer here. We do the same for hydrogen. Okay, our answer is 8.065. Again, if we round off to the nearest whole number, our answer still remains 8. So we just pick 8. Sulfur is just going to give us 1 because we're dividing by the same number. Oxygen is what we need to calculate. 3.0313 divided by 0.7563. Okay, gives us 4.00. Nice answers for all our divisions. I hope you observed the one for oxygen. It gave us 4. And our empirical formula will be N2H8SO4. This is how we can find empirical formulas using percentages, using mass. You can see the procedure is not so difficult, but we haven't yet solved the most tricky question about empirical formulas. You can stay till the end and know about more. Now let's talk about molecular formulas. Molecular formulas are very interesting. Usually these will be just given, they're the most common. They show the exact numbers of the elements in the smallest unit of a substance. For example, when you have glucose, 1 unit of glucose is always going to have 6 carbons, 12 hydrogens, 6 oxygens. That's how it is, guys. It never changes. And when we write a chemical formula that represents the number of elements for 1 unit, that's what we call a molecular formula. We can easily move from the empirical formula and get a molecular formula. For glucose, we just multiply by 6. This 6 here is what we call a factor. In this video and in this part of the video, you're going to know how to find that factor. It's not very difficult. The formula we find after multiplying an empirical formula by a factor is what we call a molecular formula. There are 3 steps again that you should follow here. They are very important. The first thing is that you should determine the empirical formula. Later in the video, I'll share with you a direct method of moving from the information to the molecular formula. But mostly, your examiner knows that people can easily go to the molecular formula directly. So they will ask you 2 questions at a time. they'll ask you to find the empirical formula and the molecular formula. So the first step is determining the empirical formula. After you have that, you need to find the factor. The factor is just a certain number that you're going to multiply the whole empirical formula by to get the actual number of elements found in 1 unit of that substance. Third and final is to determine the molecular formula. Determining the molecular formula is not difficult. You just get the factor and multiply it throughout for each element. Let's get working out so that we see how this plays out. We've got a compound here. We've been given percentage composition. You can see here there's the percentage of hydrogen, percentage of oxygen. We've also been given the molar mass. We've been asked to determine the empirical and molecular formula. Like I said, these questions will be usually combined. We've run through how to find empirical formulas. Let's get to use our knowledge we've already learned. We're going to take this percentage by mass as a mass. Therefore, hydrogen is going to have 5.9265. It's the simplest, and we're just going to copy our numerator like that. Done. We go to oxygen. Oxygen has got 94.0735. We get the 94 point that divided by 16. It equals, and we have our answer, 5.8795. We can end on the 5 there, round off using the 9, and therefore we're just going to use 5.8796. Okay, now we have the number of moles for each element. Let's divide throughout by the smallest mole, which is 5.8. The numbers are very close, but yes, there's one that is smaller. H. It's going to be 5.9265 divided by 5.8796. You can see our answer is 1.00. To the nearest whole number is just 1. I'm just going to do oxygen in advance also. You notice that because the numbers are the same there, we're not going to have any difference. You can see it gives us 1. From the calculations, you can agree with me that both our elements have got 1 in their empirical formula. So our empirical formula is just HO. This is not a molecular formula, so we can't conclude that this compound is hydroxide. We need to find the factor. To find the factor, we are going to divide the molecular mass by the empirical formula mass. The empirical formula mass is just the formula mass for the empirical formula. We get the empirical formula and use it to find a relative molecular mass. So you can see hydrogen is 1, oxygen is 16. We add those two numbers, we get 17. Therefore, our factor is going to be 34.01468. We divide it by 17. You saw how I found that. It's just like the molecular masses we've been finding. The answer we're going to get is our factor. You can see we've got 2.0008, which just implies we have 2 as our factor. Okay, now since we have the factor, we're just going to get our molecular formula by multiplying the empirical formula by the factor. So we write the empirical formula, HO, then outside the brackets we put our factor. And just like we know when we do this in chemistry, it means this 2 is multiplied by both these elements. And to write this further, we can say the molecular formula is equal to H2O2. This compound in chemistry is hydrogen peroxide actually. Let's look at a second example very quickly. This question is very interesting and will be a bit longer, so I'm going to use the whole screen. We've been told an oxide of chromium is found to have 8.1% chromium and 51.9% of oxygen. We've been asked to determine the empirical formula and the molecular formula. Well, the empirical formula is not something difficult. By now, we just get this percentage and treat it as mass. Chromium is 52. We perform the division on our calculator and we have the number of moles for chromium. You can see it's 0.925. Okay, now we do the same for oxygen. Oxygen is 51.9. We divide it by 16. Always note to use one single unit. Oxygen is diatomic in nature. However, we're not going to be using that diatomic nature. We're going to be using one single unit of oxygen. 51.9 divided by 16. From our answer here, I think we're just going to get 4 significant figures, 3.244. Therefore, N is equal to the answer we just agreed on. Now, we're supposed to find the simplest ratio between chromium and oxygen using this number of moles. Therefore, we're going to divide by the smallest mole, 0.9. So chromium will be given by 0.925 divided by 0.925, which just gives us 1. For oxygen, we will have a slight change here. And divide it by 0.925. Now, this is what we call interesting when we're finding empirical formulas. We have 3.5. When we have numbers that have got 0.5, we never make the mistake of rounding off to get a 4. Hear me right. We never round off such answers that have a 0.5 to give us a 4. We just get them as they are. As you can see, for this question, we're lucky enough to even have a 0 after the 5. Therefore, we're just going to get the 3.5. Even if we round off to one decimal place, we just have a 3.5. What are we going to do with this 3.5? Well, what this entails is that there's a probability that this compound we're trying to find the empirical formula for has some odd numbers in it. An odd number is that number which, when you divide by 2, is going to give you a remainder. So when we divide odd numbers by 2, from the definition we can get that we're going to have a remainder. Therefore, those formulas which have got odd numbers in them, when they're divided by 2, usually they give these ratios with points. And so we're going to treat them like this. We are going to look at this same number which has got a point. It's got a 0.5, right? What number can we multiply by this 3.5 to make it a whole number? Well, I think we can multiply it by a 2, and we're going to have a certain number that will be not having any points. Let's try 3.5 by 2. Okay, it gives us 7. Nice and easy. Now, some people might say, let me get 3.5 times 4. It also gives me a whole number. Well, note that if I get this number, I can divide 14 by 2 and get a simpler number. Therefore, the number that you multiply this decimal point answer should always be the simplest form. So what happens here is we get this empirical formula which is not yet built up into the right way, and then multiply it by 2. Therefore, our CR there, or the chromium, is going to be 2. The oxygen will have 7. Now let's try finding the factor. The factor is found by dividing the molecular mass by the empirical formula mass. The empirical formula mass is gotten from the empirical formula. We're going to get 2 atoms of chromium and multiply them by their relative atomic mass, and do the same for oxygen, and we add those 2 numbers, we're going to get the relative molecular mass of chromium. And because we use the empirical formula, we term that mass as the empirical formula mass. What you're going to find here, if you found your empirical formula mass correctly, is that we're going to have 216 and 216. Wow, right? So it simply implies our factor is going to be 1. Whenever this happens, you know that my empirical formula is the same as the molecular formula. However, you can continue. You put the 1, you say molecular formula is equal to empirical formula multiplied by the factor. Then you say Cr2O7 multiplied by 1, which changes nothing. So it's kind of like wasting time in your exam. Time is precious when you're writing an exam. So when you see this trend, the molar mass being equal to the empirical formula mass, just know empirical formula is the same as the molecular formula. This case is usually common when you have a formula with odd numbers. For example, 7, 5, 11. Compounds involving such numbers are usually just going to have the same molecular formula and empirical formula. If you divide that odd number, you're going to have a decimal point answer. You have successfully reached the bonus tip section. In this video, we've got 2 tips for you. The first one, as you can see, is getting a bit quick. Earlier in this video, I said there's a quick way of getting to the molecular formula. Well, how do you do that? The first thing to knowing if this is possible, you should check for the question only asking you to find the molecular formula. If your question asks you to find the empirical formula, then the molecular formula, you can never use this method. You lose marks, obviously, because the method that you get the empirical formula by using moles takes a certain marks. After you've seen that your question only asks for the molecular formula, you need to check if your elements have been given as percentages. For example, we had 21.2% of nitrogen somewhere in the examples, and yeah, you check for that. After that, then you're going to go to step 2. You find the mass of each element using percentage composition and determine the number of moles. What does this second step mean? Well, you remember when we were talking about percentage composition, we were able to find the mass of a certain compound. For example, that particular example 2, we were able to find the mass of aluminium oxide in the aluminium ore. So that is the similar procedure we're going to do here. We're going to use that percentage, multiply it by the molar mass, so that we get the grams of that specific element that are found in the molar mass. Now, why this works is because the mass we're going to find is going to be the exact mass in 1 unit of that substance. Therefore, the number of moles we're going to get is going to be a ratio of the exact numbers and not simplified numbers. Therefore, we're going to get our molecular formula straightforward. An example here is given so that you can try out. This example here is the same one we've had somewhere in this video. If you look at the values, they are the same. And what you notice is that our question only asks us to determine the molecular formula of this compound. So what you do is you multiply this percentage by this molecular mass, and the mass that you have, you use it to find the number of moles. Those moles you find, when you divide by the simplest or the smallest mole, you are going to find that the answers it gives you will be directly H2 or 2. Try this out so that you can get to know faster ways of doing things. Tip 2 is about rounding off. When you're finding your empirical formulas, it's very important to be careful when rounding off, especially when you're rounding off and you have a number that has got a decimal point greater than 2. If it's something like 1.1, 1.2, you can round off and forget about that 2. In short, that 2 or that 1 is not going to affect your whole number. Next, you should be very careful when you're rounding off your answers that are bigger than 2 actually. For example, when you have 1.5, don't try rounding off like we did in this video. If you have 1.6, 1.7, don't round off. This is because these numbers can easily be gotten rid of. For example, Just like we had the 1.5, we were able to multiply by a 2 and we had a 7. For 1.6, it's the same thing. You can find the number that you can multiply by 1.6 and it gives you a whole number, the same as 1.7. However, you'll be lucky that sometimes such situations won't be given to you. Thanks for watching to the end. Make sure you check the description for some time codes and other linked materials. And don't forget to comment down in the comment section so that we can get to interact.